Imagine standing at the edge of something so vast that the very idea of crossing it collapses every framework you have for understanding distance. Not the distance between cities, not the distance between continents, not even the distance between worlds or between our sun and its nearest stellar neighbour. Something fundamentally larger than all of that. Something so wide and so deep and so ancient that a beam of light, the fastest thing that physics permits to exist, would need 100,000 years of uninterrupted travel to cross it from one side to the other. And yet this is not some remote cosmic structure, billions of light years away. This is home. This is the galaxy we live in. This is the Milky Way. Tonight, we are going to ask a question that sounds deceptively simple. How long would it take us to cross our own galaxy? Not in a theoretical sense, not with hypothetical physics that may never exist, but with the actual technology we have built, the actual spacecraft we have launched, the actual engines we have developed over the entire span of human spaceflight history. We are going to take that question seriously, work through it with precision, and discover that the answer is not just large, it is so incomprehensibly, almost offensively large, that by the time we arrive at the final number, something about how you understand your own existence in this universe will have quietly shifted. But here is what makes this exploration even more extraordinary than it might first appear. Along the way, we are going to discover something unexpected about the galaxy itself, something about its true size that scientists did not fully appreciate until very recently, something that changes the calculation in a way that makes an already impossible number even harder to hold in the mind. We are going to encounter the limits of human ambition, the ceiling of our current physics, and the strange philosophical territory that opens up when you take seriously the prospect of attempting to cross the Milky Way with machines built by human hands. And in that territory, something profound is waiting. A question about what we are, what exploration means, and whether the attempt to cross an uncrossable distance might be the most human thing we have ever imagined doing. Keep that question close. We will come back to it. If you find yourself genuinely astonished by what follows, consider sharing this with someone else who is curious about the universe. It helps this kind of long-form, deeply researched exploration reach the people who will appreciate it most. Now, let us begin at the beginning. Let us begin with where we are. Our Sun sits in an unremarkable position within the Milky Way galaxy, roughly 26,000 light-years from the galactic center, situated in a minor spiral structure called the Orion Arm, a modest spur of stars and gas tucked between two larger spiral arms known as the Perseus Arm and the Sagittarius Arm. The Sun is not near the center of the galaxy. It is not near the edge. It occupies a kind of galactic middle ground, a position that astronomers sometimes describe as the galactic suburbs. This matters because when we talk about crossing the galaxy, we have to decide where the crossing starts and where it ends. If we begin at our current position and travel in the most direct path through the galactic center to the opposite edge, we are talking about a journey of roughly 100,000 light-years. That number, 100,000 light-years, is the figure most commonly cited as the diameter of the Milky Way, and it has been the standard reference point in astronomy textbooks and popular science writing for decades. But that number, as we will discover in careful detail later in this exploration, is no longer considered accurate. The Milky Way is bigger than we thought, considerably bigger, and the story of how we came to understand just how much bigger is itself a revelation that recontextualizes every intuition you might have about the scale of our home galaxy. For now, hold the number 100,000 light-years as a starting point, a floor rather than a ceiling, and understand that even this minimum estimate is almost beyond reckoning. 1 light-year is the distance that light travels in a single year, moving at approximately 186,000 miles per second. In a single year, a beam of light covers roughly 5.9 trillion miles. That is 5.9 followed by 12 zeros. If you were to drive from New York to Los Angeles and back again, roughly 2 billion times, you would cover approximately 1 light-year. The Voyager 1 spacecraft, humanity's most distant artificial object, has been traveling away from Earth since 1977 and has covered, as of the time this script was written, somewhere in the neighborhood of 23 billion kilometers. That is roughly 157 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. So Voyager 1 is about 157 times the Earth-Sun distance from home. Now, consider that 1 light-year is approximately 63,000 astronomical units. Voyager 1, after nearly half a century of continuous travel, has covered less than 0.3% of a single light-year. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light-years away. At Voyager, one's current speed of roughly 38,000 miles per hour, it would take approximately 73,000 years to reach Proxima Centauri if it were headed in that direction, which it is not. And the diameter of the Milky Way is at minimum 100,000 light-years. Let that settle for a moment. Let the arithmetic do its quiet work. 73,000 years to cover 4.2 light-years, 100,000 light-years to cross the galaxy. We are not talking about a longer version of the same journey. We are talking about a ratio so extreme it barely makes sense to call them both journeys. And yet this is precisely the calculation we are going to make. We are going to take the best spacecraft humanity has ever built, the fastest propulsion systems we have ever developed or seriously proposed, and we are going to ask, rigorously, how long would it actually take? The answer will be so staggering that a part of you will want to dismiss it. Resist that impulse. The staggering nature of the answer is itself the most important thing we can learn from this exercise. It tells us something true and humbling and ultimately beautiful about our place in this structure we call home. Before we can begin calculating travel times, we need to understand the galaxy we are attempting to cross with some precision. Because the Milky Way is not simply a disk of uniform stars that you can traverse in a straight line, point your engines forward and go. It is a structured, dynamic, violently active environment with regions of extraordinary density, regions of near emptiness, a massive black hole at its center that warps the very fabric of space-time in its vicinity, enormous fountains of radiation and magnetic field activity, and a halo of dark matter and ancient stars that extends far beyond the visible disk. Any honest accounting of a galactic crossing has to grapple with what the galaxy actually is, not just how wide it appears in photographs. The Milky Way is classified as a barred spiral galaxy. The barred part refers to a dense, elongated structure of stars and gas that cuts through the galactic center, oriented roughly at a diagonal to the plane of the spiral arms. This bar stretches approximately 27,000 light-years from end to end. The spiral arms, including the major ones called Norma, Sagittarius, Perseus, and the one we live near, the Orion arm, wind outward from the ends of this bar like water spiraling off the edge of a spinning wheel. The visible disk of the Milky Way, the part we can detect most readily in visible light, spans somewhere between 100,000 and 120,000 light-years in diameter. The disk itself is not uniform in thickness. Near the center, in the region surrounding the galactic bar, the disk swells into what astronomers call the galactic bulge, a roughly spherical concentration of older stars that rises about 6,000 light-years above and below the plane of the disk. As you move outward from the center, the disk thins. In our region of the galaxy, roughly 26,000 light-years from the center, the disk is approximately 1,000 light-years thick. Further out, it becomes thinner still. Embedded within this disk are roughly 200 billion to 400 billion individual stars. The range in that estimate is worth noting. We cannot count our own galaxy's stars directly. We cannot take a census. We can only measure the galaxy's total mass, account for what we know about different stellar populations and their typical masses, and derive an approximate range. The uncertainty spans 200 billion stars. That uncertainty alone, the margin of error in our stellar census, contains more suns than our best estimates of the number of galaxies in the observable universe. Between the stars lies the interstellar medium, a thin but pervasive mixture of gas, mostly hydrogen and helium, and dust. In our region of the galaxy, the density of this medium is extremely low by human standards, averaging roughly 1 atom per cubic centimeter. For reference, the air you are breathing right now contains approximately 10 to the power of 19 molecules per cubic centimeter, a number so much larger that the interstellar medium, by comparison, qualifies as the best vacuum that any laboratory on Earth has ever achieved. And yet, this near vacuum is not nothing. Over the vast distances of a galactic crossing, even this thin medium has physical consequences for any spacecraft attempting to travel through it. The galactic center is a place unlike anything in our stellar neighborhood. At its heart sits Sagittarius A star, a supermassive black hole with a mass approximately 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury around the Sun. The environment immediately surrounding this black hole is one of the most energetically extreme in the galaxy. X-rays, gamma rays, and intense magnetic fields permeate the central parsecs. Enormous jets of energized material periodically erupt from the galactic center, sending streams of radiation thousands of light-years into the halo above and below the disk. Any trajectory that takes a spacecraft through the galactic center region would require extraordinary shielding against this radiation environment, or an alternative path that skirts the central few thousand light-years entirely. Above and below the disk, extending in a roughly spherical distribution to radii of 150,000 light-years or more, lies the stellar halo, a sparse population of ancient stars and globular clusters, dense spherical collections of hundreds of thousands of stars that formed in the early history of the Milky Way. These globular clusters orbit the galactic center in elongated, often highly inclined paths, and provide some of our best evidence about the early structure and mass distribution of the galaxy. Beyond even the stellar halo, extending to radii that may reach 300,000 light-years from the galactic center, lies the dark matter halo, a vast invisible scaffolding of mass that does not emit or absorb light, but whose gravitational influence shapes every orbit in the visible galaxy. We know it is there. We have never directly detected it. We cannot say with certainty what it is made of. These are the features of the environment we are proposing to cross. not a featureless void, but a structured, complex, dangerous, and awe-inspiring system of matter, energy, and gravity. And crossing it, even at the speed of light, would take 100,000 years minimum. But we are not travelling at the speed of light. We have never come remotely close to travelling at the speed of light. The fastest objects ever created by human civilization are barely a rounding error compared to the speed of light, and understanding exactly how slow they are with real precision and not just vague hand-waving is where this exploration becomes viscerally real. Let us start with Voyager 1, launched on September the 5th, 1977 from Kennedy Space Center in Florida aboard a Titan IIIe Centaur rocket. Voyager 1 was designed for a grand tour of the outer solar system. Its primary mission was to fly by Jupiter and Saturn, study those planets and their moons, and return unprecedented scientific data. What nobody fully anticipated, or at least what nobody could publicly celebrate at the time, was that Voyager 1 would keep going. After its Saturn encounter in 1980, it received a gravitational assist that bent its trajectory upward relative to the plane of the solar system, sending it on a path out of the solar system entirely, tilted at approximately 35 degrees above the ecliptic plane. For more than 4 decades, Voyager 1 has been the fastest human-made object ever launched into interstellar space. Its current speed is approximately 38,000 miles per hour, which is also approximately 17 kilometers per second. Both of those numbers sound impressive in isolation. They are not impressive relative to what we need. 38,000 miles per hour is roughly 50 times the speed of a commercial airliner. It is fast enough that if you pointed it at the moon, it would arrive in about 6.5 hours. It is fast enough to cross the continental United States in about 5 minutes. It is not even remotely close to fast enough to cross the galaxy in any time frame that contains meaning for biological creatures like us. At 38,000 miles per hour, a journey of 100,000 light-years would take approximately 1.8 billion years, not million, billion. 1.8 billion years. The Earth is 4.5 billion years old. 1.8 billion years ago, the most complex life on Earth was single-celled organisms. Multicellular life had not yet emerged. The continents were arranged in configurations that bear no resemblance to the familiar map we know. The Milky Way has made roughly one complete orbit of its own center, approximately every 220 million years. At Voyager 1 speed, a galactic crossing would span roughly 8 of those full galactic orbits. The spacecraft and everything about it would be unrecognizable as a human artifact long before reaching any meaningful fraction of the distance. But Voyager 1 represents only our current baseline. It is not our fastest possible technology. It is not even close to the fastest technology humans have ever seriously proposed. And understanding the full range of what we might theoretically achieve, from the modest improvements already underway to the audacious engineering proposals that push right up against fundamental physical limits, is what the next chapter of this exploration demands. Because here is what makes this question so rich, so philosophically loaded, and so relevant to every ambition humanity has ever expressed about reaching the stars. The question of crossing the galaxy is not just an engineering problem. It is a question about the nature of time, about the relationship between civilization and duration, about what it even means to undertake a journey that no individual, no generation, no civilization as currently constituted could survive to complete. It forces us to ask what kind of entity could make such a journey, and whether any such entity would still bear any meaningful relationship to the humans who first pointed it toward the far side of the Milky Way. That is the deeper question threading through everything we are about to explore, and it will not let go. The most obvious next step beyond Voyager 1 is to ask what we have built since 1977 that goes faster. The answer, in the context of deep space travel, is both encouraging and sobering. Encouraging because we have indeed developed propulsion technologies that significantly exceed Voyager 1's speed. Sobering because even our fastest achieved velocities and the fastest plausible near-term advances barely move the needle when measured against the scale of the galaxy. The fastest human-made object ever recorded by peak velocity is not Voyager 1. That distinction belongs to the Parker Solar Probe, a spacecraft launched by NASA in August of 2018 with the specific mission of flying closer to the Sun than any previous human artifact. The Parker Solar Probe uses a series of Venus gravity assists to gradually tighten its orbit around the Sun, bringing it progressively closer to the solar surface with each successive pass. During its closest approaches, the spacecraft is moving at extraordinary speeds due to the Sun's immense gravitational pull. In November of 2021, during one of its early perihelion passes, the Parker Solar Probe reached a speed of approximately 364,000 miles per hour. That is roughly 0.054% of the speed of light. It is nearly 10 times faster than Voyager 1. It sounds like a genuine leap forward. At 364,000 miles per hour, a crossing of 100,000 light-years would take approximately 182 million years. That is meaningfully shorter than the 1.8 billion years we calculated for Voyager 1, in the sense that dividing by 10 is mathematically meaningful. But 182 million years is still an almost incomprehensible span of time. 182 million years ago, the first dinosaurs had only recently appeared on Earth. The supercontinent Pangaea was still in the process of breaking apart. Flowering plants did not yet exist. To call 182 million years a journey duration is to use the word journey in a sense that has no precedent in any human experience. And the Parker Solar Probe's speed is not a sustainable cruise velocity. It achieves those peak speeds only at the closest point of its highly elliptical solar orbit, where the Sun's gravity is doing most of the work of acceleration. It is not carrying enough propellant to sustain that velocity as a baseline speed through interstellar space. Once it leaves the solar system, if it were directed outward as a hypothetical interstellar probe, it would be traveling at something much closer to Voyager 1's speed. The solar speed record is real, but it is not a template for interstellar travel. So what would a genuine next-generation interstellar propulsion system look like? What technologies exist or have been seriously proposed that could actually change the calculus in a meaningful way? This is where the engineering gets genuinely fascinating, and where the gap between what we have and what we need becomes one of the most instructive measurements in all of science. The most straightforward improvement on chemical rocket propulsion is nuclear thermal propulsion. The basic concept has been understood since the 1950s and was actively developed in the United States under programs with names like NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. The idea is straightforward. Instead of burning chemical propellants like liquid hydrogen and liquid oxygen to generate thrust, you use the heat from a nuclear reactor to superheat a propellant, typically hydrogen, and expel it through a nozzle at much higher velocities than chemical combustion allows. The exhaust velocity of a nuclear thermal rocket is roughly twice that of the best chemical engines, which means you can extract significantly more velocity change from the same mass of propellant. Nuclear thermal rockets could, in principle, allow spacecraft to reach speeds several times higher than Voyager 1's cruise velocity in interstellar space. Estimates vary depending on design and mission architecture, but speeds on the order of 100,000 to 150,000 miles per hour are considered plausible for a nuclear thermal spacecraft on an optimized trajectory. This would reduce our galactic crossing time from 1.8 billion years to perhaps 500 million years. Still impossibly long. Still longer than the entire history of complex multicellular life on Earth. But the trend is pointing in a direction, and where the trend points becomes interesting. The more dramatic leap comes with nuclear pulse propulsion, a concept that dates to the late 1950s and was developed in remarkable seriousness under a project called Orion, not the constellation or the NASA crew vehicle, but a classified and later declassified defense research program that explored using nuclear explosions as a propulsion mechanism. The basic concept of nuclear pulse propulsion is that a spacecraft ejects small nuclear devices behind it, detonates them, and uses a massive shock-absorbing pusher plate at the rear of the spacecraft to capture the momentum of the explosion and convert it into forward thrust. The physics of this approach, while extreme, are sound. Nuclear explosions release energy in quantities that dwarf anything achievable through chemical or even conventional nuclear thermal means. A spacecraft using nuclear pulse propulsion could, depending on the design and the yield of the devices used, potentially achieve speeds of several percent of the speed of light. Early Orion studies suggested that a spacecraft using thermonuclear pulse units, which are substantially more energetic than pure fission devices, could reach speeds of 3 to 5% of the speed of light on a sufficiently extended journey with enough devices aboard. 3 to 5% of the speed of light is approximately 22,000 to 37,000 miles per second. It is an extraordinary number by human standards. At 3% of the speed of light, you could travel from Earth to the Moon in less than half a second. At 5% of the speed of light, the journey from Earth to Mars at average orbital separation would take a matter of minutes rather than months. But now, let us apply that speed to the problem of galactic crossing. At 5% of the speed of light, crossing 100,000 light years would take 2 million years. 2 million years. Homo sapiens as a species has existed for only about 300,000 years. Our genus Homo, stretching back to Homo habilis and the earliest stone tool makers, reaches back perhaps 2.5 million years. A journey at 5% of the speed of light across the Milky Way would span roughly the entire evolutionary history of the human lineage. The civilization that launched the spacecraft would be unrecognizable or more likely extinct long before the spacecraft covered even a fraction of the distance, and 5% of the speed of light represents an extraordinarily optimistic near-term projection. It assumes solving engineering problems of extraordinary complexity, including the miniaturization and safe storage of thousands or millions of nuclear devices aboard a single spacecraft, the development of materials capable of withstanding repeated nuclear detonations at close range, and the international political agreements necessary to deploy nuclear weapons in space, which are currently prohibited by treaty. None of these problems are insurmountable in principle, but none of them are trivially solved either. There is a concept further along the propulsion spectrum that represents perhaps the most thoroughly analysed approach to genuine interstellar travel within the laws of physics, as we currently understand them. It is called a Bussard ramjet, and it was proposed in 1960 by the physicist Robert Bussard. The concept is elegant and audacious in equal measure. As a spacecraft moves through interstellar space, it encounters the thin interstellar medium, primarily hydrogen. What if the spacecraft could scoop up that hydrogen as it travelled, using an enormous electromagnetic funnel to collect interstellar protons, and then fuse them in an onboard fusion reactor to generate thrust? Rather than carrying all its propellant with it, the spacecraft would harvest fuel from the medium it was travelling through. The faster it went, the more hydrogen it could collect per second, potentially allowing it to accelerate continuously toward a significant fraction of the speed of light. The appeal of the Bussard ramjet is immense. It seems to offer a path to relativistic travel, meaning travel at a significant fraction of the speed of light, without the need to carry the enormous fuel mass that conventional rocket physics demands. Conventional rocketry faces a brutal constraint known as the Tsiolkovsky rocket equation, which describes the relationship between a rocket's mass, its propellant mass, and the velocity it can achieve. The equation is unforgiving. To double your final velocity, you need to roughly square the ratio of propellant mass to spacecraft mass. Achieving 10% of the speed of light with a conventional rocket requires a propellant-to-payload mass ratio so extreme that the spacecraft is almost entirely propellant, with a vanishingly small payload at the center. Achieving 20% of the speed of light compounds the problem further into the realm of the physically impractical. The Bussard ramjet sidesteps this constraint entirely, in theory, but subsequent analysis by physicists including Tony Martin and Robert Zubrin in the 1970s and 80s identified serious problems with the original concept. Proton-proton fusion, the reaction that powers stars like our Sun, is extraordinarily slow at the densities and temperatures achievable in a practical reactor. The Sun itself takes tens of billions of years to fuse protons at the core because the proton-proton reaction rate is inherently sluggish. A spacecraft reactor attempting to fuse interstellar hydrogen in real time would almost certainly lose more energy to the drag of scooping the medium than it could gain from the fusion of what it collected. The ramjet, in its original form, appears to be fundamentally limited by this drag versus gain problem. Modified versions of the concept, including a variant proposed by Zubrin called the magnetic sail or magsail, and another called the RAM-augmented interstellar rocket, attempt to work around these limitations in various ways. These modified designs shift from pure interstellar hydrogen fusion to carrying some conventional fusion fuel and using the RAM scoop primarily for additional propellant rather than as the sole energy source. Whether these modified concepts can achieve what the original promised remains an open and genuinely unresolved question in theoretical astronautics. Now consider the concept that has attracted the most rigorous scientific attention as a near-term pathway to interstellar probes, not crewed ships, but small robotic probes at genuinely high fractions of the speed of light. This concept is laser propulsion, and its most publicly prominent recent incarnation is the Breakthrough Starshot initiative, announced in 2016 by a coalition of scientists and philanthropists including the late Stephen Hawking and the physicist Yuri Milner. The Breakthrough Starshot concept begins with a fundamental insight about the Tsiolkovsky rocket equation. The reason conventional rockets face such punishing propellant requirements is that they must carry their own energy source with them. What if the energy source stayed home? What if you accelerated a spacecraft using a beam of energy transmitted from Earth or from Earth orbit rather than from onboard propellant? This is the principle of beam-powered propulsion, and laser-driven light sails represent its most developed form. In the Starshot concept, a fleet of extremely tiny spacecraft, each one roughly the mass of a large paperclip, perhaps a few grams, would be attached to an ultra-thin reflective sail a few meters across. An array of ground-based or space-based lasers, with a combined output in the gigawatt range, would fire a concentrated beam of light at the sail. The photons in the laser beam carry momentum, and when they reflect off the sail, they transfer that momentum to the spacecraft. Because the spacecraft is so light, even the relatively tiny momentum of reflected photons could accelerate it to extraordinary speeds. The Starshot proposal envisions accelerating these tiny spacecraft to approximately 20% of the speed of light. At 20% of the speed of light, the nearest star, Proxima Centauri, would be reachable in roughly 20 years. That is a revolutionary prospect for interstellar exploration, but let us apply 20% of the speed of light to the problem of galactic crossing. At 20% of the speed of light, crossing 100,000 light-years would take 500,000 years. 500,000 years. This is meaningfully shorter than the 2 million years we calculated for nuclear pulse propulsion at 5% of light speed. It is incomparably shorter than the 1.8 billion years for Voyager 1. But 500,000 years is still 500,000 years. Modern humans have been anatomically modern for roughly 300,000 years. The entire span of recorded human history, from the earliest cuneiform tablets of Sumerian civilization to the present moment, spans approximately 5,000 years. 500,000 years contains 100 of those entire recorded histories stacked end to end, one after another. A civilization that launched a laser-sail spacecraft toward the far side of the Milky Way today would have to wait 500,000 years to receive any signal confirming arrival, assuming the spacecraft carried communications equipment capable of transmitting across that distance. The civilization that received that confirmation would bear roughly the same relationship to us as we bear to the early Homo sapiens of 300,000 years ago, who hunted with stone tools and had not yet developed symbolic language as we understand it today. And we are still discussing speeds that the Breakthrough Starshot project, one of the most ambitious and well-funded interstellar initiatives in history, considers the outer boundary of near-future technological possibility. We have not yet invoked the speculative physics. We have not yet discussed concepts that require breakthroughs in our fundamental understanding of nature. We are still within, or at least near, the envelope of what current physics permits with currently understood engineering approaches. But those speculative concepts exist, and they are worth examining carefully, because they are the only pathways that reduce the galactic crossing time to something that might theoretically be accomplished within a time frame meaningful to a civilization, if not to an individual. And examining them requires confronting what our current understanding of physics says about the ultimate limits of velocity. The absolute speed limit of the universe, as far as we know, is the speed of light in a vacuum, approximately 186,000 miles per second, or about 671 million miles per hour. This limit is not an engineering constraint that better technology might someday overcome. It is a fundamental feature of space-time as described by Einstein's special theory of relativity published in 1905. The theory has been tested with extraordinary precision across a vast range of experiments and observations over more than a century. Every test has confirmed it. No object with mass can be accelerated to the speed of light. As an object's velocity approaches the speed of light, the energy required to accelerate it further approaches infinity. You could pour the entire energy output of the Sun into accelerating a spacecraft, and it would not reach light speed. You could pour the energy output of all the stars in the galaxy, and it would still not reach light speed. The limit is absolute. But special relativity contains a provision that sounds, at first encounter, almost too strange to be real. As an object moves at velocities approaching the speed of light, time itself, as experienced by that object, slows down relative to time as experienced by stationary observers. This phenomenon is called time dilation, and it is not a quirk or an approximation or a metaphor. It is a measured, confirmed, routinely accounted for feature of reality. The GPS satellites orbiting Earth move fast enough that their onboard clocks run slightly slow relative to clocks on the ground. Without correcting for this effect, GPS navigation would accumulate errors large enough to make the system useless within hours. At low velocities, the time dilation effect is tiny. At 90% of the speed of light, a traveller experiences time passing at roughly 44% of the rate that stationary observers experience it. At 99% of the speed of light, the traveller's time runs at about 14% of the external rate. At 99.9% of the speed of light, the traveller's time slows to about 4.5% of the external rate. The closer you get to light speed, the more dramatic the effect becomes, approaching zero at exactly light speed, which is why nothing with mass can reach it. This means that in principle, a spacecraft travelling at a sufficiently high fraction of the speed of light could cross the galaxy in a time that is manageable from the perspective of the crew aboard the ship, even while hundreds of thousands of years pass for the rest of the universe. At 99.9999% of the speed of light, the time dilation factor approaches 1,400. A journey of 100,000 light years would take about 71 years as experienced by the crew, a human lifetime. Just barely. There it is. The first number in this entire exploration that fits inside a human life. And it required getting a spacecraft to 99.9999% of the speed of light. The energy required to accelerate even a modest spacecraft to that velocity is not just large, it is cosmically large. The kinetic energy of a 1,000 kilogram spacecraft, roughly the mass of a small car, moving at 99.9999% of the speed of light, is approximately 1.3 times 10 to the power of 23 joules. The total energy output of the Sun, integrated over an entire year, is approximately 1.2 times 10 to the power of 34 joules. So accelerating our small spacecraft to that velocity would require a substantial fraction of the Sun's annual energy output. The Sun produces that energy by fusing roughly 600 million tons of hydrogen per second in its core through a process that has been running for 4.6 billion years. Capturing, storing, and directing even a small fraction of that output is so far beyond current technology that calling it a future engineering challenge feels almost quaint. But here is what makes this specific number worth sitting with for a moment. It is not infinite, it is large, but it is a finite quantity of energy. Physics does not forbid this journey. Physics merely makes it extraordinarily, breathtakingly expensive. There is a difference between impossible and merely very, very hard. That difference matters enormously when you are trying to understand what the universe will and will not allow. The distinction between forbidden and merely difficult is one of the most important in all of science, and right now we are operating on the difficult side of that line. Everything we have discussed so far, Voyager 1, nuclear propulsion, laser sails, relativistic flight, is difficult. Sometimes absurdly, civilization transcendingly difficult. But none of it violates known physics. None of it requires discovering that the universe works differently than we currently believe. What comes next does. There is a class of theoretical concepts for crossing cosmic distances that does not rely on going faster. It relies instead on making the distance shorter, or on stepping outside normal space-time altogether. These concepts belong to a different category of speculation, one that requires not just better engineering, but new physics. And understanding them, understanding both their theoretical basis and their extraordinary practical obstacles, is essential to a complete accounting of what a galactic crossing might or might not look like for a civilization with ambitions larger than its current technology. We will get to those, but before we do, we need to revisit something mentioned earlier, something held in reserve. We said that the diameter of the Milky Way is at minimum 100,000 light-years, and that this number is no longer considered accurate. The galaxy, it turns out, is larger than we thought. The story of how we discovered this, and how large the revision actually is, changes every calculation we have made so far in a way that demands attention. For most of human history, we had no idea we lived in a galaxy at all. The concept that the faint band of diffuse light stretching across the night sky, the one that ancient Greeks called the Milky Circle and ancient Chinese astronomers called the Silver River, represented an enormous disk of hundreds of billions of stars, was not established until the 20th century. And even after that establishment, our estimates of the galaxy's size have been revised repeatedly, almost always in the same direction, almost always upward. The first serious attempt to map the Milky Way came from the British-German astronomer William Herschel in the late 18th century. Herschel spent years counting stars in different directions across the sky, reasoning that the more stars he could see in a given direction, the further the galaxy extended in that direction. His maps, produced through extraordinary observational labour, showed a flattened disc-like structure, with the Sun near the centre. The methodology was sound in its basic logic. The conclusion was wrong in almost every particular, not because Herschel lacked skill or dedication, but because he did not know about interstellar dust. The interstellar medium is not just gas. It contains microscopic solid particles, grains of carbon, silicate minerals, ices, and complex organic molecules that scatter and absorb visible light. In our region of the galaxy, this dust is unevenly distributed, but pervasive enough to significantly limit how far we can see in the plane of the galactic disk using visible light. Herschel was counting stars through a medium that grew progressively more opaque at greater distances without knowing it was opaque at all. His counts tapered off in all directions at roughly similar distances, not because the galaxy ended there, but because the dust blocked his view beyond that range. The Sun appeared to be near the centre of the galaxy, because the dust limited his sight equally in all directions from his vantage point. The actual distance from our Sun to the galactic centre was not established until the early 20th century, primarily through the work of the American astronomer Harlow Shapley. Shapley studied globular clusters, those dense, spherical collections of ancient stars that orbit the galaxy in elongated paths. He noted that globular clusters were not distributed randomly across the sky. They were concentrated in one hemisphere of the sky, heavily toward the constellation Sagittarius. If the Sun were at the center of the galaxy, the globular clusters should be distributed roughly evenly in all directions. Their concentration toward Sagittarius meant the true center of the galaxy was in that direction, and the Sun was displaced from it by a significant distance. Shapley's estimates of that distance were substantially larger than the modern accepted value. He placed the Sun roughly 50,000 light-years from the galactic center, compared to the modern measurement of approximately 26,000 light-years. But his fundamental insight, that the Sun was not at the center and that the true center was in the direction of Sagittarius, was correct, and represented a genuine revolution in our understanding of our place in the cosmos. It was, in a quiet way, a Copernican moment. First, the Earth was removed from the center of the solar system. Now the solar system was removed from the center of the galaxy. Through the middle decades of the 20th century, our maps of the Milky Way improved steadily. Radio astronomy, developed after World War II, transformed galactic mapping by providing a tool that could penetrate the interstellar dust that blocked visible light. Radio waves pass through dust clouds with minimal absorption, allowing astronomers to detect hydrogen gas, the most abundant component of the interstellar medium, across enormous distances using its characteristic emission at a wavelength of 21 centimeters. By mapping the distribution and motion of this hydrogen gas, astronomers could trace the spiral structure of the galaxy with far greater reach than optical surveys allowed. These radio surveys confirmed the spiral structure of the Milky Way and refined the estimate of its diameter to approximately 100,000 light-years for the main stellar disk. That figure became the standard reference repeated in textbooks, popular science articles, and documentaries for decades. The Milky Way is 100,000 light-years across. That was the number. That was what we thought we knew. But the full extent of a galaxy is not simply the extent of its most obvious, easily detected component. The bright, dense stellar disk that we see in optical and radio surveys is not the whole galaxy. It is the most visible part. And as observational technology improved, astronomers began to detect structures associated with the Milky Way that extended far beyond the boundaries of the conventional disk. The stellar halo, that sparse population of ancient stars and globular clusters surrounding the disk, was known to extend well beyond the disk's edge. But how far? Early estimates placed the outer boundary of the stellar halo at somewhere around 100 to 150,000 light-years from the galactic center. Beyond that, the stellar density appeared to drop off steeply and the galaxy seemed to end. But ended for what, exactly? The stars thinned out. The gas thinned out. But the dark matter, the invisible gravitational scaffolding that holds the galaxy together and dominates its total mass, did not thin out nearly as quickly. Measurements of the rotational velocities of stars and gas clouds at different distances from the galactic center revealed that the galaxy's gravitational influence extended far beyond the visible disk. Stars at the outer edges of the disk were orbiting the galactic center faster than they should be if the only mass present were the visible stars and gas. Something additional, something invisible, was providing extra gravitational pull. That something is what we call dark matter, and its presence extends the effective gravitational boundary of the Milky Way to radii far larger than the visible disk. The full extent of the dark matter halo surrounding the Milky Way is one of the most actively debated questions in modern galactic astronomy. Estimates have placed its outer boundary at anywhere from 150,000 to over 300,000 light-years from the galactic center. The uncertainty is large because detecting the outer boundary of a dark matter halo requires either tracing the orbits of extremely distant objects, like satellite galaxies or isolated stars in the far halo, or using sophisticated gravitational modeling that depends on assumptions about the mass distribution. Neither approach gives a clean, unambiguous answer. But the more dramatic revision to our understanding of the Milky Way's size did not come from dark matter studies. It came from surveys of the stellar disk itself, and it came from a direction that researchers did not fully anticipate. In the 1990s and 2000s, a series of wide-field sky surveys using charged coupled device detectors, which are the same technology underlying modern digital cameras but scaled up to astronomical instruments, began detecting stars at the outer edges and beyond the nominal boundary of the galactic disk. These surveys were not specifically designed to find the edge of the Milky Way. They were conducting broad census work across large patches of sky, cataloguing the positions and brightnesses of hundreds of millions of stars. But in the data, patterns emerged. One of the most striking was discovered in a survey called the Sloan Digital Sky Survey, a project that began in 2000 and used a dedicated telescope at Apache Point Observatory in New Mexico to image roughly a third of the entire sky and catalogue the properties of hundreds of millions of galaxies and stars. Astronomers analysing Sloan data noticed a broad, diffuse stream of stars in the outer regions of the galaxy that did not fit the expected distribution. These stars were not part of a globular cluster or a known satellite galaxy. They were spread across an enormous arc of sky, suggesting they were part of a structure much larger than any known cluster. This feature became known as the Monoceros ring, and it appeared to be a ring of stars wrapping around the outer disk of the Milky Way at distances of 60,000 to 80,000 light-years from the galactic center. The origin of the Monoceros ring is still debated. Some astronomers believe it represents the tidally disrupted remnant of a small dwarf galaxy that was absorbed by the Milky Way billions of years ago, its stars stretched into a ring-like structure by the gravitational forces of the encounter. Others argue that it represents an actual outer extension of the galactic disk itself, a warped and flared outer rim that extends well beyond what was previously mapped. The distinction matters enormously for questions of galactic size. The warp of the Milky Way's outer disk is itself a well-established observational fact. The disk is not perfectly flat. Moving outward from the Sun, the disk begins to curve upward on one side of the galaxy and downward on the other, like the brim of a hat that has been bent slightly. This warp was known for decades, but its extent and amplitude at large radii were not fully appreciated until comprehensive surveys of the outer disk became available. In 2019, a team of astronomers published an analysis based on data from over 100,000 Cepheid variable stars, a class of pulsating stars whose intrinsic brightness is directly related to their pulsation period, making them extraordinarily reliable distance indicators. By mapping the positions of these Cepheid variables across the full extent of the galaxy, the researchers produced the most detailed three-dimensional map of the galactic disk ever constructed. What they found was a disk that was not just warped, but significantly more extended than the conventional 100,000 light-year estimate. The outer disk, including its warp and flare, extended to radii of at least 60,000 light-years from the galactic center on the far side, suggesting a total disk diameter closer to 120,000 light-years in conventional terms. But the outer flare, the region where the disk thickness increases dramatically at large radii, contains stars at even greater distances. A study published in 2020 using data from the European Space Agency's Gaia satellite, which has been mapping the positions and motions of nearly 2 billion stars with extraordinary precision since its launch in 2013, pushed this further. The Gaia data revealed a population of stars at the outer edge of the disk that extended to distances of over 80,000 light-years from the galactic center on the far side. Combined with the known extent on the near side and accounting for the position of the Sun, this suggested a disk diameter potentially approaching 200,000 light-years when the full, flared outer disk is included. But the most striking recent revision came not from disk surveys, but from work on the very outer reaches of the galaxy's stellar population. In 2023, a team led by researchers at the University of California, Santa Cruz published an analysis of the distribution of stars in the extreme outer galaxy, at distances of several 100,000 light-years from the galactic center, using data from multiple sky surveys. They found that the boundary between stars that are gravitationally bound to the Milky Way and those that are not, a boundary called the splashback radius, or virial radius, extended to approximately 1 million light-years from the galactic center. 1 million light-years, not 100,000, not 200,000, 1 million. At that scale, the Milky Way is not the relatively modest spiral galaxy of textbook fame. It is a structure so vast that its gravitational dominion encompasses a sphere 2 million light-years in diameter, a region large enough to contain the Andromeda Galaxy, our nearest large galactic neighbor, within its sphere of influence before Andromeda's own gravity asserts clear dominance. This does not mean the Milky Way is 2 million light-years across in the sense of stellar density. The bright disk, the part we see in photographs, remains roughly 100,000 to perhaps 200,000 light-years in its visible extent. But the full dynamical extent of the galaxy, the region where the Milky Way's gravity is the dominant force shaping the motion of matter, reaches 1 million light-years out. Now recalculate every journey time we have discussed. At Voyager 1 speed, crossing 1 million light-years from one dynamical boundary of the Milky Way to the other would take approximately 18 billion years. The universe itself is only 13.8 billion years old. Voyager 1, at its current speed, could not cross the full extent of our own galaxy's gravitational domain within the entire current age of the universe. It would need more time than the universe has existed to make the journey. At 20% of the speed of light, the most optimistic near-term laser sail velocity, crossing 1 million light-years would take 5 million years. Not the 500,000 years we calculated for the visible disk, but 5 million. The entire span of hominid evolution, from our earliest upright walking ancestors to the present moment, spans approximately 5 to 7 million years. A laser sail crossing the full dynamical extent of the Milky Way would take as long as the evolutionary journey from Australopithecus to you. These numbers are not presented to discourage or to suggest futility. They are presented because understanding the true scale of what we inhabit is itself one of the most important things we can do as thinking creatures trying to understand their place in the cosmos. We live in something far larger than we knew, and the full reckoning of that scale has implications that extend far beyond the question of travel times. Consider for a moment what it means to be inside a structure 1 million light years across and not know it. For most of human history, we did not know we lived in a galaxy at all. Then we discovered we lived in a galaxy roughly 100,000 light years across. Then we revised that to include the halo and got perhaps 300,000 light years. Now, including the full dynamical extent, we are at 1 million light years. Each revision has been in the same direction. Each revision has made the home larger. This pattern should give us pause about assuming the current estimate is final. But here is something even more arresting. Even if we use only the conventional visible disk diameter of 100,000 light years, even if we ignore the dark matter halo, ignore the stellar halo, ignore the outer disk flare, ignore the dynamical boundary entirely, and focus purely on the bright spiral disk that hosts the vast majority of the galaxy's stars, including our Sun, we are still confronting a structure whose crossing at the speed of light alone would take 100,000 years. Light itself, the universal speed limit, needs 100,000 years to make the journey. And we have never built anything that travels at the speed of light. We have never come close. Our fastest spacecraft travels at roughly 0.005% of the speed of light. The gap between what we can do and what would be required is not a gap that ambition and determination alone can bridge. It is a gap that may require either an entirely different relationship to time than biological creatures currently have, or an entirely different approach to distance than conventional propulsion allows. Both of these possibilities deserve serious examination, and they point in directions that are philosophically as much as technically radical. The relationship to time question brings us to something that science fiction has explored for decades, but that serious scientists have also thought carefully about, which is the nature of a generation ship. The basic concept is that a spacecraft does not need to be fast enough for a single crew to survive the journey if the journey is instead planned across multiple generations. A ship large enough to sustain a self-sufficient human community indefinitely could, in principle, carry the descendants of its original crew across arbitrary distances, provided the ship remains functional and the community remains viable. A generation ship crossing the galaxy at Voyager 1 speed would be in transit for 1.8 billion years. That is not a generation ship in any meaningful sense. No community, no matter how well designed and maintained, could sustain biological or cultural continuity across 1.8 billion years. But at a more optimistic speed of 1% of the speed of light, which is itself far beyond our current capability, a crossing of the 100,000 light-year visible disk would take 10 million years. Still longer than the entire history of our genus, but now at least in a range where we can think about it in biological terms rather than geological ones. At 10% of the speed of light, 1 million years. At 20% of the speed of light, 500,000 years. Each of these numbers represents many thousands of generations of humans. The original crew would be ancestral to the eventual crew, in the same way that the first anatomically modern humans who left Africa are ancestral to all non-African populations today. The cultural, linguistic, cognitive and biological distance between departure and arrival would be incalculably vast. And yet the generation ship concept represents a kind of philosophical commitment that is worth taking seriously on its own terms. It says that a journey does not need to be completed within a single lifetime or a single civilization's span to be worth beginning. It says that the act of committing to a direction of pointing a community of humans toward a destination that only their descendants will reach is itself a meaningful act. It says that the galaxy might be crossable not by any individual or any civilization as currently constituted, but by the continuous thread of human descent sustained across time frames that are vast even by cosmic standards. There is something both humbling and strangely moving about that idea. The longest journey ever attempted by a biological species, measured not in miles or years, but in generations, in the accumulated experiences of 10,000 successive human lifetimes, all pointed in the same direction, all contributing to a single voyage that none of them would see completed. But before we follow that thread of thought to its full philosophical implications, before we sit fully with what it means that even our most ambitious biological strategies face such enormous obstacles, we need to examine the other category of solution. The one that does not try to go faster or endure longer, but instead asks whether the distance can be made irrelevant, whether the geometry of space-time itself might offer shortcuts that conventional physics, read too narrowly, seems to forbid. This brings us to the concept of warp drives, wormholes, and the genuinely strange landscape of what general relativity technically permits, even if it does not necessarily provide. And understanding this landscape requires a brief detour into the nature of space-time itself, because the concepts only make sense against the backdrop of what Einstein's general theory of relativity actually says about the structure of the universe we inhabit. General relativity, published in 1915, describes gravity not as a force in the Newtonian sense, but as a curvature of space-time caused by the presence of mass and energy. A massive object like the Sun does not reach across space and pull on the Earth. Instead, the Sun's mass curves the fabric of space-time around it, and the Earth follows the straightest possible path through that curved space-time, which happens to be an elliptical orbit. The rubber sheet analogy, where a heavy ball placed on a stretched sheet creates a depression that smaller balls roll toward, is familiar but misleading in important ways. Space-time is not a two-dimensional sheet. It is a four-dimensional continuum, and the curvature is not a metaphor. It is a physical reality that has been measured with extreme precision. General relativity has a remarkable property. Its equations describe the geometry of space-time given a distribution of mass and energy. But the equations are silent about what specific mass-energy distributions are physically realizable. They describe what geometry would result from a given distribution, but they do not, by themselves, forbid exotic distributions. And some exotic distributions produce exotic geometries, geometries that look, from a human perspective, deeply strange. One of the most famous exotic solutions to Einstein's equations is the wormhole, first seriously analyzed by Einstein himself and his colleague Nathan Rosen in 1935. An Einstein-Rosen bridge, as it is properly called, is a solution to the field equations that connects two distant regions of space-time through a shortcut that bypasses the ordinary space between them. Imagine folding the rubber sheet so that two distant points are brought close together, and then punching a tube through the fold that connects them. A traveller entering one mouth of the tube would emerge at the other mouth, having effectively traversed the intervening distance without passing through the space in between. The mathematics of wormholes is genuinely part of established general relativity. The concept is not fringe physics. It appears in peer-reviewed journals, in university cosmology courses, in the work of theorists including Kip Thorne, who shared the Nobel Prize in Physics in 2017. But the mathematical existence of a solution to the field equations does not mean that solution describes anything that actually exists or can be constructed. And here is where the wormhole concept runs into its deepest problems. The wormhole solutions found in general relativity are almost universally unstable. A traversable wormhole, one that a spacecraft could actually pass through, requires something that does not obviously exist in nature. It requires a form of matter with negative energy density. Not just matter with negative charge or negative spin, matter with a genuinely negative energy density, meaning it gravitationally repels rather than attracts, and whose stress-energy tensor has components that violate what physicists call the energy conditions. Ordinary matter, in all the forms we have ever observed, obeys these energy conditions. It has positive energy density. It gravitates in the ordinary attractive way, something called the Casimir effect. A quantum mechanical phenomenon in which two very closely spaced metal plates in a vacuum experience a tiny attractive force due to modifications in the vacuum's quantum field, fluctuations, does produce a form of negative energy density in the narrow gap between the plates. The Casimir effect is real and has been measured, but the scale of the negative energy produced is fantastically small, and whether it can be harnessed and concentrated into the quantities needed to stabilize a macroscopic, traversable wormhole is a question that current physics cannot answer, and which most physicists regard with deep skepticism. The warp drive concept faces a structurally similar problem. In 1994, the Mexican physicist Miguel Alcubierre published a paper describing an exact solution to Einstein's field equations in which a spacecraft could travel faster than light without locally exceeding the speed of light. The trick was elegant. Rather than accelerating the spacecraft itself, the Alcubierre metric involves contracting spacetime in front of the spacecraft and expanding it behind, creating a wave of space-time distortion that carries the spacecraft in a bubble, like a surfer riding a wave. Inside the bubble, the spacecraft is locally at rest. It is the bubble itself, the warp of space-time, that moves, and general relativity places no speed limit on the movement of space-time itself. The mathematics of the Alcubierre metric is valid. It is a genuine solution to Einstein's field equations. A civilization that could create and maintain an Alcubierre warp bubble could, in principle, cross the galaxy in any desired time, including hours or days. It could traverse 100,000 light-years before breakfast. And it also requires exotic matter with negative energy density. An enormous quantity of it. Early estimates of the negative energy required to create an Alcubierre bubble were staggering, on the order of the mass energy equivalent of the planet Jupiter, but in negative form. Later refinements of the concept by Harold White and others at NASA reduced the theoretical requirements substantially through modifications to the bubble geometry, but the exotic matter requirement did not disappear. It only became less astronomically vast. It remained physically unprecedented. We have never observed exotic matter with negative energy density at macroscopic scales. We do not know whether it exists. We do not know whether the universe permits it in the forms required by warp drive or wormhole physics. These are not engineering problems in the conventional sense. They are open questions about the fundamental structure of reality. They may be resolved by future physics. They may turn out to be genuinely forbidden. we do not currently know which. What we do know is that every shortcut through space-time that general relativity seems to permit comes with a requirement that nature may or may not honor. And we have not yet found nature being particularly generous with exotic matter. There is one more approach worth examining before we turn from the physics of transit to the deeper question of what a galactic crossing would mean for the entity attempting it. This approach does not require exotic matter. It does not require wormholes or warp drives. It requires instead a different way of thinking about the travelers themselves. Because so far we have been assuming that the travelers are biological human beings, or at least biological organisms descended from human beings. We have been assuming that the journey must be compatible with human physiology, human psychology, human cultural continuity across time. We have been assuming, in other words, that the crossing of the galaxy must be a human story in some recognizable sense. But what if it is not? The question of whether the crossing of the galaxy must be a human story in any recognizable sense is not a rhetorical flourish. It is the most practically significant question in this entire exploration. Because when you examine the numbers honestly, when you sit with the travel times we have calculated without flinching away from their implications, you arrive at a conclusion that is uncomfortable but inescapable. Biological humans, as currently constituted, cannot cross the galaxy. Not in any meaningful sense, not even close. The gap between our biological lifespan and the shortest crossing time achievable with plausible near-future technology is so enormous that no individual, no dynasty, no cultural tradition could bridge it while remaining recognizably human in the way we currently understand that word. But civilizations do not stay the same. They change. They develop, they transform themselves. And the kinds of transformation that would be required to make a galactic crossing possible are themselves worth examining with the same rigor and precision we have applied to the propulsion physics. Because the story of how a civilization might reach the far side of the Milky Way is not just a story about rockets and fuel and velocity. It is a story about what that civilization might have to become in order to attempt the journey at all. The most conservative approach to extending the viable timeline of travelers is suspended animation, or, more precisely, the induction of a state of dramatically reduced metabolic activity that would allow a biological organism to survive indefinitely without aging or consuming resources. The concept has deep roots in science fiction, where it is usually depicted as a simple technological solution, a pod you climb into and wake up from decades later, no worse for the passage of time. The reality is considerably more complicated. True, suspended animation for humans does not currently exist. What does exist is a set of techniques that extend this basic concept in limited ways and provide some evidence that the underlying biology might not be impossible. Therapeutic hypothermia, the deliberate cooling of a patient's body to reduce metabolic rate and protect tissue from damage during surgery or after cardiac arrest, is standard medical practice. Bodies cooled to approximately 27 to 30 degrees Celsius experience dramatically slowed metabolic processes and can tolerate interruptions to blood flow that would be fatal at normal body temperature. Some surgeons have extended this concept to what they call emergency preservation and resuscitation, cooling patients to as low as 10 degrees Celsius to buy time for surgery on otherwise lethal trauma. In nature, certain animals achieve states of metabolic suppression during hibernation that far exceed anything medical hypothermia approaches. Bears reduce their metabolic rate to roughly 25% of normal during winter hibernation. Ground squirrels reduce theirs to as low as 1 to 2%. Their body temperatures drop to just above freezing. Their heart rates fall to a few beats per minute, and they can sustain this state for months without significant tissue damage. The mechanisms behind this extraordinary capability involve complex biochemical changes that researchers are only beginning to understand, including modifications to cell membrane composition, changes in enzyme activity, suppression of the immune system's inflammatory responses, and alterations in the regulation of cellular energy production. Whether these mechanisms could be replicated, amplified, and applied to humans to produce genuine long-duration suspended animation is genuinely unknown. Some researchers believe the biology is not fundamentally different between hibernating mammals and humans, and that the relevant genetic and biochemical pathways might be activatable in human cells with sufficient understanding. Others argue that the differences are too deep and too structural to bridge. The honest answer is that we do not yet know. But even if we assume suspended animation is achievable, even if we imagine a technology that could pause a human body's aging indefinitely and revive it perfectly after any duration, we still face the problem of the ship. A spacecraft carrying suspended humans across the galaxy must remain functional for millions of years. Its systems must continue operating, its navigation must remain accurate, its life support must remain intact, its shielding against radiation and micrometeorite impacts must hold, and its ability to revive the crew at the destination must be preserved across timescales that dwarf the entire span of recorded civilization. No human-made machine has ever operated continuously for more than a few decades without maintenance. The Voyager probes, our most durable spacecraft, require ongoing monitoring and periodic adjustments by teams of engineers on Earth. They have been degrading slowly since launch and are expected to lose the ability to communicate with Earth sometime in the late 2030s, roughly 60 years after launch. A spacecraft designed for millions of years of autonomous operation is not an engineering challenge of the same type as a spacecraft designed for decades of operation. It is an entirely different category of problem. The materials science alone is daunting. Every material we know of degrades over time. Metals corrode, crystallize, fatigue, and fracture. Polymers degrade and become brittle. Electronic components experience electromigration, diffusion of metal atoms through conductors that eventually causes circuit failure, at rates that depend on temperature and current density, but that accumulate inevitably over time. Radioactive decay of trace elements within materials causes radiation damage to surrounding structures. Even in the cold, radiation-rich environment of interstellar space, a spacecraft operating for 1 million years faces material degradation challenges that no current engineering framework is equipped to address. The software and computational infrastructure of such a ship would face equally daunting challenges. No software system ever created has operated error-free for more than years without human intervention. Cosmic rays, high-energy particles that permeate interstellar space, cause bit flips in digital memory, single events where a stored 0 becomes a 1 or vice versa, corrupting data and potentially causing catastrophic software failures. At the radiation fluxes encountered in interstellar space, unshielded electronics would accumulate bit flip errors rapidly. Heavy shielding reduces but cannot eliminate this problem. Error-correcting codes can catch and fix many errors, but introduce their own complexity and potential failure modes. A system that must operate autonomously for 1 million years while self-correcting its own software and hardware failures is a profoundly unsolved engineering problem. These obstacles do not make the concept impossible in principle. They make it extraordinarily, perhaps prohibitively, difficult with any technology that resembles what we currently possess. They suggest that a civilization capable of launching a successful crewed galactic crossing would need to have solved engineering problems that are not just incremental advances over current practice, but represent qualitative transformations in materials, science, manufacturing, computing, and autonomous systems. And this observation points toward the more radical possibility. Perhaps the solution to the galactic crossing problem is not to make ships that last millions of years while carrying sleeping humans. Perhaps the solution is to change what it means to be the traveler. Consider the concept of digital consciousness uploading, the hypothetical process of scanning a human brain at sufficient resolution to capture its functional organization, and transferring that organizational pattern into a computational substrate. The idea is deeply controversial, both scientifically and philosophically. We do not currently know whether human consciousness is the kind of thing that can be computationally emulated. We do not know whether a computational emulation of a brain would be conscious in any meaningful sense, or whether it would simply be a very sophisticated simulation that behaves as if conscious without any inner experience. These are questions that neuroscience and philosophy of mind are nowhere near resolving. But set those philosophical uncertainties aside for a moment and examine the engineering implications. A digital mind, if such a thing were possible, would have extraordinary advantages as a galactic traveler. It would not age. It would not require food, water, or breathable atmosphere. Its subjective experience of time could be adjusted either by running its computational processes faster or slower than normal, or by pausing them entirely during transit. A digital traveler moving at 5% of the speed of light across 100,000 light-years would experience 2 million years of ship time, unless its processes were suspended, in which case it would experience no subjective time at all. It would be as if the journey took no time from the traveler's perspective, like dreamless sleep, with the traveler simply ceasing to exist subjectively at departure and resuming at arrival. The computational substrate carrying the digital mind would need to survive the same millions of years of interstellar travel that a crewed ship would. The durability problem does not disappear, but the redundancy options available to a digital system are far greater than those available to a biological one. A biological human cannot be copied. A digital mind, if the underlying philosophy permits copying, could be stored in thousands of redundant copies across a distributed system, each checking the others for errors, with the entire ensemble drifting through interstellar space over millions of years. If 99% of the copies were destroyed by a catastrophic event, the remaining 1% could reconstruct the whole. The resilience of a sufficiently redundant digital system to time and damage could, in principle, exceed anything achievable with biological systems. But here is the philosophical problem that cannot be set aside indefinitely. A digital mind that has its processes suspended for 2 million years and then reactivated is not, in any experiential sense, a traveler. It did not experience the journey. It did not endure the time. It simply stopped being and started again, in a different place. In what sense is the entity that wakes up at the far side of the galaxy the same entity that went to sleep near the Orion arm? Is identity preserved through suspension? Does it matter? These are not merely philosophical puzzles. They are practically important questions for any civilization seriously considering a galactic crossing program, because the answer determines what the crossing actually means. If identity is not preserved through suspension, then the galaxy is not being crossed by any individual. It is merely being reached by a copy, a descendant, a continuation in some sense, but not in the sense of personal continuity that we normally mean when we say someone has travelled somewhere. And this brings us to something that has been threading quietly through this entire exploration, surfacing occasionally and then submerging, but never fully resolved. It is the question of what a galactic crossing is for. What is the purpose? What would it mean to succeed? And does the answer to that question change when we honestly reckon with what the journey would cost and what the traveller would have to become in order to complete it? We set out to ask how long it would take to cross the Milky Way. We have been answering that question with increasing precision and increasing humility. But the numbers have been telling us something beyond themselves. Something about the relationship between scale and meaning, something about the nature of ambition when it meets a universe that is profoundly, fundamentally indifferent to the timescales of biological life. Pause for a moment on this. The Milky Way did not form at a speed compatible with human experience. It did not assemble its spiral arms on a schedule anyone could witness in a lifetime. The stars within it are born and live and die on timescales of millions to billions of years. The galaxy rotates once every 220 million years. These are not the timescales of civilizations or of species. They are the timescales of geology, of stellar evolution, of planetary formation. The galaxy operates on a clock that has no face we can read, and yet here we are inside it, conscious, curious, pointing our instruments at it and asking questions about its structure and size, building machines and launching them into the void, calculating travel times as if the crossing were a project that could be planned and budgeted and completed. There is something both magnificent and slightly absurd about this. Magnificent because the attempt to understand is itself extraordinary. Slightly absurd because the scale of what we are contemplating so vastly exceeds our actual capabilities that the contemplation itself might seem like a kind of cosmic overreach. But is it? Consider the alternative. Consider what it would mean for a species to look at the galaxy it inhabits and simply not ask the question, to note the scale and turn away, satisfied with the verdict of impossibility before the investigation has properly begun. That kind of intellectual surrender has never been how the best human thinking operates. The history of exploration is not a history of waiting until the journey was easy before attempting it. It is a history of attempting journeys that seemed impossible, and finding that impossibility, properly examined, often conceals a narrow path that ambition and ingenuity can navigate. The ocean crossings that seemed impossible, the mountain heights that seemed unsurvivable, the barrier of sound that seemed unbreakable, the void between Earth and the moon that seemed unbridgeable. Each of these was genuinely dangerous, genuinely uncertain, genuinely beyond the comfortable reach of the technology of its time. Each was crossed anyway by people who decided that the crossing mattered more than the comfort of staying home. But the Milky Way is different from all of those, not just in degree, but potentially in kind, because none of those crossings required the travellers to stop being human in the process. None of them required the dissolution of individual identity across millions of years of suspended time. None of them required the transformation of flesh into digital patterns, or the replacement of biological descendants with engineered successors, so transformed from their ancestors as to share only the most abstract, thread of continuity. The crossing of the galaxy, if it is ever accomplished, will probably not be accomplished by humans. It will be accomplished by whatever humans become. And understanding what that might mean requires confronting the deepest question this exploration has been building toward since the first section. Not how long would it take, not even how could it be done, but whether the entity that completes the crossing would still be, in any sense that matters, us. That question has an answer. It is not a comfortable answer. It is not a simple answer, but it is one of the most important answers that thinking about the galaxy demands of us. And to arrive at it properly, we need to understand one more thing about the Milky Way that we have not yet fully examined. Something about its future, about what the galaxy will be when or if any civilization manages to cross it. Because the galaxy we are discussing is not a static backdrop. It is moving. It is changing. It is heading somewhere. And where it is heading changes everything about the context of a galactic crossing in a way that adds one final layer of staggering scale to everything we have already considered. The Milky Way is on a collision course with the Andromeda Galaxy. Andromeda, also known by its catalogue designation Messier 31, is the nearest large galaxy to the Milky Way, currently located approximately 2.5 million light-years from us. It is visible to the naked eye from dark sky locations as a faint smudge of light in the constellation Andromeda, appearing roughly 6 times the width of the full moon in angular extent, though most of its light is too faint to see without optical aid. It is a barred spiral galaxy, broadly similar to the Milky Way, containing approximately 1 trillion stars, roughly twice to 3 times the number in our own galaxy, and spanning approximately 220,000 light-years in diameter. For most of the 20th century, astronomers debated whether Andromeda was approaching the Milky Way or moving away from it, and at what velocity. Measuring the motion of a galaxy along the line of sight is relatively straightforward using the Doppler effect, the shift in the wavelength of light caused by the motion of a source toward or away from an observer. Andromeda's light is blue-shifted, meaning it is moving toward us. The radial velocity, the component of motion directly along our line of sight, has been measured at approximately 110 kilometers per second of approach. But radial velocity alone does not tell you whether 2 galaxies will collide. A galaxy approaching directly head-on will collide. A galaxy approaching at a glancing angle might miss entirely, or pass nearby without merging. The critical measurement is the transverse velocity, the component of motion perpendicular to the line of sight. Measuring transverse velocities of objects at millions of light-years distance is extraordinarily difficult because the apparent motion across the sky is vanishingly small, even over decades of observation. The Hubble Space Telescope finally resolved this question with a series of observations spanning several years, measuring the extremely subtle proper motion of stars in Andromeda across the sky. The results, published in 2012, confirmed that Andromeda is on a direct collision course with the Milky Way. The transverse velocity is small enough that the 2 galaxies will not pass each other by. They will merge. The collision is expected to begin in approximately 4.5 billion years. But calling it a collision in the ordinary sense is deeply misleading. Galaxies are not solid objects. They are mostly empty space. The average distance between stars in both galaxies is measured in light-years. When 2 galaxies merge, the stars almost never actually collide with each other. The probability of any individual star directly striking another during the merger is vanishingly small. What does collide, in a sense, is the gravitational structure of the two galaxies. The dark matter halos interpenetrate. The gravitational fields interact. The stars are flung into new orbits by the combined gravitational forces, and the gas clouds in both galaxies collide and compress, triggering enormous bursts of new star formation. The merger of the Milky Way and Andromeda, which astronomers have named Milkomeda or sometimes Milkdromeda, will unfold over billions of years. The first close pass will distort both galaxies dramatically, flinging stars into long tidal streams. The galaxies will swing past each other, separate and fall back together over the course of several billion years before finally settling into a merged elliptical galaxy, a roughly spherical concentration of stars with no spiral structure remaining. What does this mean for a civilization attempting to cross the Milky Way? If the crossing takes millions of years at even optimistic velocities, and if the Andromeda merger begins in 4.5 billion years, the two timescales are not obviously incompatible. A crossing begun today at 20% of the speed of light would take 500,000 years to cross the visible disk. 4.5 billion years from now, that crossing would have been possible to complete and repeat 9,000 times over. The merger does not impose an immediate deadline on galactic crossing ambitions, but it does recontextualize the nature of the home being crossed. The galaxy we are discussing as the object of this impossible journey is itself temporary. In 5 to 10 billion years, it will no longer exist as a distinct structure. The Milky Way will have been absorbed into Milkomeda, its spiral arms long since disrupted and dispersed, its stars scattered into new configurations by the violence of the merger. The home that any civilization might aspire to cross will itself be gone before any plausible crossing is completed by anything resembling our current technology. This is the kind of temporal vertigo that the galaxy induces when you look at it honestly and completely. Nothing is fixed. Nothing is permanent. Not our sun, which will exhaust its hydrogen fuel in approximately 5 billion years and expand into a red giant that engulfs the inner planets. Not the Milky Way itself, which will cease to exist as a recognizable structure on a similar timescale. Not even the stars of the merged Milkomeda galaxy, which will gradually burn out over trillions of years until the last red dwarf fades and the universe enters a long, dark, cold era of stellar remnants and eventually evaporating black holes. We are asking how long it would take to cross our own galaxy in a universe that is itself running a clock that, on timescales long enough to make a galactic crossing meaningful, is ticking toward endings that dwarf any journey we might plan. The question of crossing the Milky Way, pursued to its logical conclusion, becomes a question about time itself, about what we mean by home when home is impermanent, about what we mean by journey when the destination may not exist when the traveller arrives. These are not comfortable conclusions. They were not meant to be. They are the honest conclusions that follow from taking the question seriously, from refusing to truncate the inquiry at the point where the numbers stop being convenient. And sitting with them, really sitting with them, is where this exploration was always headed. There is a particular kind of silence that descends when you have followed a chain of reasoning far enough that it stops being about facts and starts being about what the facts mean. We have arrived at that silence. We have calculated the crossing times. We have mapped the galaxy's true extent. We have examined every propulsion concept from chemical rockets to warp drives. We have confronted the merger with Andromeda and the impermanence of the galaxy itself. We have asked What kind of entity could make the journey, and found that the answer points away from anything we currently recognize as human. Now we need to ask the question that all of this has been building toward. Not how long, not how, but why. Why does a species that cannot cross its own galaxy, that may never cross its own galaxy in any recognizable form, keep asking whether it could? What does that persistent asking reveal about us? And is there something in the asking itself, regardless of whether the answer ever becomes yes, that matters in a way the numbers cannot capture? Begin with what we know about the history of human exploration. Not as a catalogue of achievements, but as a pattern of motivation. Every great expansion of human presence into new environments has been driven by a mixture of practical necessity and something harder to name. The practical necessities are easy to identify: resources, survival pressure, economic incentive, competition between groups. These are real and have genuinely driven exploration throughout history, but they are not sufficient explanations. They do not account for why humans keep going further than necessity requires, why the boundary of the known has always exerted a pull that exceeds any rational cost-benefit analysis of the territories beyond it. The Pacific Ocean was the largest barrier human beings ever crossed before the modern era. The islands of the Pacific were settled by Polynesian navigators over a period spanning roughly 3,000 years, beginning perhaps 3,500 years ago and reaching its final frontier, the Hawaiian Islands and New Zealand, roughly 1,000 years ago. These crossings were made in outrigger canoes using navigational techniques based on stars, ocean swells, wind patterns, and the behavior of birds, without any of the instruments we associate with reliable deep-sea navigation. The distances involved were staggering by the standards of pre-modern technology. The crossing from the Society Islands to Hawaii covers roughly 4,000 kilometers of open ocean with no intermediate landmarks. From eastern Polynesia to New Zealand, roughly 4,500 kilometers in a different direction. Why did they go? The practical answers are real: population pressure on small islands, the need for new agricultural land, conflict driving groups to seek new territories. But those answers do not fully explain the systematic, multi-generational project of island discovery that Polynesian culture sustained across 3 millennia. At some point, the motivation was not just necessity. It was the knowledge that there was more ocean and the refusal to leave it unexplored. That same pattern appears in every sustained episode of human exploration. The motivation that carries a civilization beyond necessity and into genuine frontier territory is not purely practical. It is something closer to what the philosopher Blaise Pascal described when he wrote that all of humanity's problems stem from the inability to sit quietly in a room alone. The inverse of that observation is equally true. Some of humanity's greatest achievements stem from the inability to stay in the known room when there is an unknown room next door. The galaxy is the largest unknown room we have ever become aware of, and we have been unable collectively to look at it and feel nothing. Every culture that developed sufficient astronomy to recognize the Milky Way as a structure has had myths, stories, and cosmologies that placed it at the center of meaning. The Maori of New Zealand saw it as a river of light, Te Aho a Maui, Maui's fishing line. The ancient Egyptians associated it with the goddess Nut, the sky itself. The Norse saw it as Bifrost, the bridge between worlds. Long before anyone knew what the galaxy was, humans were already telling stories about it, already treating it as a place that connected the world they inhabited to something larger and more mysterious. The scientific revolution did not diminish this impulse, it amplified it. When we learned that the Milky Way was not a river of light, but a galaxy of 200 to 400 billion stars, not a feature of our sky, but a structure we were inside, not a boundary, but a home of incomprehensible scale, the stories did not stop. They became more urgent. The myths did not die. They transformed into questions. How big? How old? What is at the center? Are there other beings inside it asking the same questions from different vantage points among the stars? The question of whether we could cross the galaxy is not, at its root, an engineering question. It is an expression of this ancient and apparently ineradicable human relationship with the unknown horizon. It is the Pacific Ocean impulse operating at the largest possible scale. It is the refusal to accept that because something is very far away and very hard to reach, it is therefore not worth thinking about reaching. And here is what that impulse has achieved, even when it could not achieve the thing it was aimed at directly. The attempt to understand whether the galaxy could be crossed has generated some of the most profound scientific knowledge humans have ever produced. The development of radio astronomy to map the galactic structure that we could not see through the dust. The construction of the Gaia satellite that mapped the positions of nearly 2 billion stars in 3 dimensions and revealed the true extent of the outer disk. The theoretical work on nuclear pulse propulsion that, though never built for interstellar travel, advanced our understanding of nuclear physics and aerospace engineering. The analysis of wormhole solutions to Einstein's equations that deepened our understanding of general relativity and the nature of space-time. The debates about digital consciousness and personal identity that the generation ship concept provokes, which are among the most serious philosophical inquiries into the nature of mind that our era has produced. The attempt to cross the galaxy, even when it fails, even when it remains theoretical, generates knowledge. It generates it by forcing us to take seriously the full scale of what we inhabit. It generates it by demanding that our theories be complete enough, our instruments precise enough, our imaginations expansive enough to grapple with the real dimensions of home. The galaxy does not reward small thinking. Every serious attempt to understand it requires expanding the frameworks we use to understand everything else. But there is a harder and more personal version of this argument that deserves its moment. Set aside the scientific returns, set aside the engineering spin-offs and the philosophical insights. Ask simply this: what is the experience of a conscious being who genuinely reckons with the scale of the galaxy it inhabits? Not briefly, not as a fact to be noted and filed away, but deeply and completely, following the implications all the way to their ends. We have done something like that in the course of this exploration. We have followed the numbers from Voyager 1's 38,000 miles per hour to the 1 million light-year dynamical extent of the Milky Way. We have watched every crossing time we calculated exceed the span of human civilization, then exceed the span of our species, then exceed the span of complex life on Earth, then exceed the age of the universe itself. We have watched every shortcut through physics come with requirements that nature may not honor. We have watched the galaxy itself turn out to be temporary, headed for a merger that will dissolve its spiral arms into a merged elliptical remnant over billions of years. And somewhere in the middle of all that, if the reckoning has been honest, something happened to the scale at which you were thinking. Something shifted. The problems that fill ordinary human days, the anxieties and ambitions and conflicts that seem large from inside a human life, did not disappear, but they acquired a different context. They took on a different proportion relative to a structure 1 million light-years across, rotating on a clock of 220 million years, containing perhaps 400 billion suns, itself one of 2 trillion galaxies in the observable universe, itself contained within a cosmos whose age, at 13.8 billion years, is almost 3 times the age of the Earth beneath your feet. This is what genuine engagement with scale does to a mind. It does not make the small things feel meaningless, it makes them feel precisely sized. They are the right size for a human life. They fit inside a human life. They do not need to be larger, but they also do not need to pretend to be the whole story, because the whole story is incomparably larger, and knowing that incomparable largeness exists, and being one of the rare configurations of matter in the universe complex enough to know it exists, is itself a kind of astonishment that does not wear off if you let it stay with you. There is a specific number that serves as the most precise summary of everything this exploration has been about. It is not a crossing time. It is not a speed. It is a ratio. The ratio of the fastest speed ever achieved by a human-made object, the Parker Solar Probe at its perihelion, to the speed of light. That ratio is approximately 0.054%, not 5%, not 0.5%, 0.054%. 1 part in roughly 1850. We are travelling at our absolute fastest at 1/1850th of the cosmic speed limit. And even at the cosmic speed limit itself, the galaxy takes 100,000 years to cross. We are not close. We are not approaching close. We are at the very beginning of a journey toward close that may take our civilization longer than our civilization has yet existed to make any meaningful progress along. And yet, the Parker Solar Probe exists. It was designed by human minds, built by human hands, launched by human ambition, and it is right now moving through the inner solar system at 364,000 miles per hour, on a trajectory that no natural process would have produced, aimed precisely at scientific targets chosen by people who wanted to understand the sun. It exists because someone asked a question and then refused to stop asking until the question produced an answer that could be launched into space. Voyager 1 exists. It has been travelling for nearly half a century. It has crossed the heliopause, the boundary between the sun's influence and interstellar space, and it is now moving through the medium between the stars. It carries a golden record containing sounds and images selected to represent life and culture on Earth, chosen on the assumption that someday, somewhere, something might find it. The probability of that happening is vanishingly small. The people who made that choice knew the probability was vanishingly small. They made the choice anyway, because the act of reaching out mattered regardless of whether the reach was ever completed. The James Webb Space Telescope, launched in December of 2021, is currently positioned approximately 1.5 million kilometers from Earth at a gravitationally stable point called the second Lagrange point, looking outward at the universe with instruments so sensitive they can detect the infrared light of galaxies that formed when the universe was less than 400 million years old. It can examine the atmospheres of planets orbiting other stars, looking for chemical signatures that might indicate biological processes. It was designed and built and launched during a period of enormous global stress, at enormous expense, because a sufficient number of people believed that looking deeply into the universe was worth doing, even when every practical argument for diverting those resources elsewhere was available and coherent. These are not small things. They are not the achievements of a species that has accepted its limitations and turned inward. They are the achievements of a species that keeps pointing instruments and machines and questions at the largest structures it can conceive of, driven by something that does not have a clean scientific name, but that is recognizable to anyone who has ever stood under a clear night sky and felt the pull of the light coming from very far away. The question of crossing the galaxy will not be answered in our lifetimes. It will not be answered in the lifetimes of our grandchildren or their grandchildren or any number of generations we can meaningfully imagine. The crossing times we have calculated are longer than any lineage can trace, longer than any civilization has endured, longer than our species has existed. The honest answer to how long it would take to cross the Milky Way is, with current technology, longer than the universe has been old. With the most optimistic near-future technology, longer than the history of complex life on Earth. With the most speculative physics we can imagine, 500,000 years at the absolute minimum for the visible disk. And that assumes achieving relativistic velocities that dwarf anything we have ever built. These are not answers that invite action in the conventional sense. They are answers that invite a different relationship with the question itself, a relationship that is less about planning and more about understanding, less about engineering and more about reckoning, less about the destination and more about what it means to live inside a structure so vast that the mind must stretch itself to its limits to even approximate its dimensions. We live inside the Milky Way. We will almost certainly die inside the Milky Way as a species long before any technology exists to carry us beyond it. The galaxy is not a destination for us. It is our home in a sense so total and so encompassing that the word home barely contains it. We are to the Milky Way as a bacterium in your bloodstream is to you. We inhabit it at a scale so many orders of magnitude below its total scale that we are, for all practical purposes, invisible within it. 400 billion stars, and our sun is one of them. Unremarkable in size, unremarkable in age, situated in an unremarkable position in an outer spiral arm, orbiting the galactic center at a speed of approximately 500,000 miles per hour, in a journey that takes 220 million years to complete. We are small, we are brief, we are local, we are, in the most literal possible sense, provincial residents of a minor region of an average galaxy in a universe containing 2 trillion such galaxies. And we know this. That is the extraordinary thing. We are small enough to be invisible within the galaxy and complex enough to measure it. We are brief enough that the galaxy does not register our existence and curious enough to map its full dynamical extent to 1 million light years. We are local enough that the crossing time at our fastest speed exceeds the age of the universe, and imaginative enough to conceive of warp drives and wormholes and digital mines and generation ships, and every other strategy that might someday, in some unimaginable future, make the crossing possible. The universe did not have to produce anything capable of asking how wide it is. The laws of physics that govern nuclear fusion in stellar cores do not require anywhere in their structure the emergence of consciousness. The equations of general relativity that describe the curvature of space-time do not demand that any mind arise to write them down. The Milky Way has been rotating for 10 billion years, forming stars and destroying them, building spiral arms and dissolving them, capturing satellite galaxies and tearing them apart, and for almost all of that time, There was nothing anywhere in it that asked what it was, or how large it was, or how long it would take to cross it. Then, in the last 300,000 years, on a small rocky planet orbiting an unremarkable star in an outer spiral arm, something happened. Chemistry became biology. Biology became complexity. Complexity became consciousness. And consciousness, almost immediately, looked up. That looking up is what we have been doing together in the course of this exploration. We looked up and asked a question, and we followed the question honestly wherever it led, through the propulsion physics, and the galactic cartography, and the revised size estimates, and the wormhole mathematics, and the philosophical territory of generation ships and digital minds, and the impermanence of the galaxy itself. We followed it until it stopped being a question about engineering and became a question about meaning. And the meaning, if there is one, is not in the crossing. It is in the asking. It is in the refusal to accept the scale of the galaxy as a reason to stop thinking about it. It is in the Parker solar probe moving at 364,000 miles per hour through the inner solar system on a trajectory designed by human minds, and in the Voyager 1 crossing the heliopause after nearly 50 years of travel, and in the James Webb Space Telescope looking back to the edge of the visible universe with instruments made of mirrors and metal and human ingenuity. It is in every radio telescope ever pointed at the galactic center, in every Cepheid variable measured to map the outer disk, in every calculation ever made of the energy required to reach relativistic velocity. It is in this, right now, in the fact that you are here, attending to the dimensions of your home, refusing to let the scale make you look away. There is a detail from the opening of this exploration that deserves its return, now at the end, with the full weight of everything between. We noted that a beam of light needs 100,000 years to cross the visible disk of the Milky Way. Light, moving at 186,000 miles per second, the fastest thing the universe permits, requires 100,000 years to make the journey we have been contemplating. The light reaching your eyes right now from the stars in the night sky left those stars years or decades or centuries ago. The light we detect from the far side of the galactic disk left its source 100,000 years before it arrives here. We are not seeing the galaxy as it is. We are seeing it as it was. Every observation we make of distant structures is an observation of the past. The further the structure, the more distant the past we are seeing. Our maps of the Milky Way are maps of light that departed before our species existed, before our genus existed, before the last common ancestor of humans and chimpanzees walked the forests of Africa. We are, in the most literal sense, looking back in time every time we look at the galaxy. We are reading a letter written before we were born, sent across 100,000 light years of space, arriving at this small rocky planet and entering these improbable eyes, and being interpreted by these remarkable brains as a map of home. The galaxy did not send that light to us. It did not know we would be here to receive it. The stars shine in all directions equally, indifferent to whether anything is watching. But something is watching. Something looked up and built instruments to see further, and thought carefully about what it was seeing, and asked, with genuine and sustained curiosity, how large, how old, how far, and how long would it take to cross? The answer to that last question, pursued to its honest conclusion, is longer than we can meaningfully plan for, longer than we can currently survive, possibly longer than our species will exist. The crossing of the Milky Way may be beyond us in any final sense. The galaxy maybe not just the largest structure we inhabit, but the largest structure we will ever inhabit. The outer boundary of all human presence in the cosmos, the horizon that never gets closer, no matter how fast we travel. But the horizon has always been where humans look, not because we will necessarily reach it, not because the looking is guaranteed to produce arrival, but because the act of looking at the furthest thing we can see and refusing to pretend it is smaller than it is, refusing to flinch from the true scale of what surrounds us, is one of the most fully human things we have ever done. The Milky Way is 100,000 light-years across at its most conservative measurement. It is perhaps 200,000 light-years across, including the full extent of its outer disk. Its gravitational dominion reaches 1 million light-years in every direction. It contains between 200 billion and 400 billion stars. It is 4.5 billion years old in the sense of having formed its central structure in that time, but its oldest stars are nearly as old as the universe itself. It is rotating on a clock of 220 million years. It is heading toward a collision with Andromeda that will dissolve it into a merged elliptical galaxy over the next 5 to 10 billion years. And we, a species 300,000 years old on a planet 4.5 billion years old orbiting one of its 400 billion stars, have measured all of this. We have measured our own home from the inside without ever leaving it, using nothing but light and mathematics and the restless human need to know where we are and how large the place is that contains us. That is not a small thing. That may be the largest thing we have ever done.